Okay, so this is test number 7 from the series 2. This test is mainly based on lenses, because lenses, learning about lenses will be crucial to learn the next two parts, which are optical instruments and human eye. Without having a great knowledge in lenses, it is not possible to learn the next two parts. These are like linked, right? So that's why we have a separate test for lenses. And good luck and great work for those who did the test, who faced the test. Right. We'll move on to the first question. The lenses in the image are called in order. Okay. In the syllabus, we only have to deal with convex and concave lenses. But other shapes of lenses, there are some other shapes of lenses that we need to at least know how to name them, right? In when we do problems, those almost all the questions are based on biconvex and biconcave lenses, but we at least have to know how to name the different shapes of lenses, right? So these lenses, we have given these lenses, this shape and this shape and this shape, right? The key part to identify whether a lens is a convex or a concave lens, this is the part, right? So if you take a lens, this could be any shape, if these ends are less thick compared to the middle of the lens, if the middle of the lens is thicker than the edges of the lens, these types of lens we call them convex. Middle should be thicker than the edge of the lens, so they are called convex. So you can see that if middle is thinner, see here, middle is thinner, edges are thicker, so these types of lens we call them concave lenses. It could be any shape. That is the key, how you can identify whether lens is convex or concave. So if I bring that to here, so this should be a type of a convex lens because edges are thin compared to the middle. So this is a type of convex lens. First figure that out. So this is a convex lens because the middle is thicker. And if you think about like a one side, that is a plane side, so we call that plano. So this lens should be plano convex. Then this lens, edges are thicker compared to the middle, so this should be a concave lens. Since both sides have the same shape, concave shape, we call that bi, both sides. So this is biconcave. Then let's move on to this one. This is a crescent shape. This is a crescent shape, meaning that has a meniscus. This shape we call that meniscus shape. That's the shape of the moon when it is not fully shining. In some days this is the shape of the moon, so we call that shape meniscus. Okay, figure out whether this is convex or concave. Edges, middle is thicker compared to the edges, so this is convex. We call that because this shape, one of the shape is a meniscus shape. Meniscus convex, so we call that meniscus convex. So in this way, if you clearly understood what I said, you could name any type of lens like that, right? So the answer for this should be fifth one. That's the matching answer for the first question. Second question, as shown by the image, part of a lens is wrapped by a black paper. When an object is placed in front of the lens, correct sentence about the real image formed is. Okay, so this, I just drew the ray diagram here. So there's this lens. Just for a while, for a moment, just forget about this black paper, right? So this is just a lens without covering. Then we can figure out, so this is the object, so it creates a real image here, right? Like that, a real image, right? So this ray, it just goes through the center and here, then this other ray, parallel ray, it goes here through the focus. So the image of this point is created here. Image of this point is created here. We drew only these two lines to find the position of the image. So this is the position of, this is the object, this is the position of the image. That is just a position. Those two are not the only rays that's going from this point. The rays are going like to all the directions from this point. I can draw other rays like this. All these rays, since we know the position now, I can, all those rays goes towards that point in order to make the image. I can further, let's say the lens is here as well. If I draw a lens, a ray like this, that ray also would go here. So all these rays goes towards this image is here, in order to form that image, right? So the rest of the image, rest of the image also is formed similarly. If you know this top point, image of the top point is made here, we can imagine the remaining points also is formed like this, right? Then let's cover the middle part of the lens like this. So what happens? These rays cannot go through that. These rays cannot go through. But still, the image is formed using other rays. Image is formed at that place using other rays. But the number of rays that contributed to form the image here has decreased since it is covered now. So what could happen now, right? The image is still made. Nothing changes. The image is formed as it is. The shape or anything does not change just because we cover this part of a lens. What happens is, since the number of rays has decreased, the brightness of the image decreases. Now it has less number of rays forming the image. So the brightness decreases. That's what all happens, right? Same thing happens if you cover this part of the lens. The number of rays, these rays would cancel off. The number of rays would decrease, but still the image is formed without any difference. So let's check out the answers. The remaining part does not contribute forming the image. Lens forms an image and its brightness is less compared when the black paper is not there, right? So that's what happens. That's the second answer there. Only the brightness decreases. That's all that happens, right? Still the image is formed, only the brightness decreases. It is less bright now. So the answer should be the second one. Third one, in front of a convex lens with focal length 15 centimeters, when an object is placed at a distance 20 centimeters, a linear magnification of the image is, okay, so this is what happens. We have this convex lens. I'll just draw a sketch. And the focal length is given as 15 centimeters. Object is placed at 20 centimeters. So what they ask is linear magnification. So in order to find the linear magnification, we have to find the image distance, that is simple V, right? Okay, so to find the first, we have to find V. We'll use lens equation. So here U is equal to plus 20, okay, because this is the direction of light. Any measurement to the direction of light is negative, but this measurement is to the opposite side, so that should be a plus value. So just substitute that plus value here. 20 equals focal length of a convex lens is minus, so I'll just minus value. Then we have to find V. Take to the other side. Now it is a normal calculation. Once you did the substitution, then it is a simple calculation. 1 over 2, 1 over 15. So this comes to 60. Denominator is 60. So 3 here minus 4 here. Minus 1 over 60. So just flip both sides of the equation. So V is equal to minus 60 centimeters. Minus means the image is here. So it's a real image, because this is measured to the direction of light. Light is moving to this direction from the object. So it is measured to this direction, 60 centimeters. That's why we got a negative value there. We actually don't need that to get the answer, but for further clarification, that's how the sign convention works. So the next part, what they ask is a linear magnification, simple M. Linear magnification is, just to recall you this stuff, capital H divided by simple h. Capital H is the height of the image, simple h is the height of the object. Capital H divided by simple h, height of the image divided by height of the object. So this is also equal to V over U. Image distance divided by object distance, V over U. We put a modulus sign there usually. Right, now we know the value of V. Since due to the modulus sign, modulus means you only take the positive value of this. Even though this is minus 60, you can write it as 60 because of the modulus. Divide by U. U, we know that is 20. So the linear magnification of the object is 3, right? So meaning that size of the image has increased by 3 times. That's what it means to be linear magnification. How many times the image has enlarged compared to the object. So that is 3 times for this question. So the answer should be third one for the third question. Fourth question. When an object is placed in front of a lens at a distance 27 centimeters, linear magnification of virtual image is 1/4. Focal length of the lens is, right. So we'll just take down what we know. So we know the object distance, that is 27 centimeters. It is positive value. And they say linear magnification of image is 1/4 of virtual image. Right. If it is a virtual image, if you are very familiar with these lenses, and if you have practiced many questions, you should know, if virtual image is linear magnification is 1/4, size of the image has decreased. So this only can happen for a concave lens. If the object is here, the image size has decreased. This is the image, because the linear magnification is 1/4 of the object size. Image size is 1/4 of the object size. That is what it means, 1/4. So it has decreased. So if you think about these results, so this lens must be a concave lens, right? Because they say this forms a virtual image. So the image is formed at this side, not this side. If the image is formed here, it has to be a real image. But since it is formed here, this image is a virtual image, right? Okay. So we know this stuff. Then we know that then we can apply this equation, m equals v over u. So v also is positive. It is for sure v is positive. Linear magnification 1/4. V is what we need to find. U we know that is 27. So v is 27/4 centimeters. This is the value of image distance, 27/4. Right. But what they ask is focal length of the lens. So to find that, we will use lens equation. So this is 1/v. V means 27/4 minus 1/u, that is 27, equals 1/f. From here as well you can check whether this is a convex lens or a concave lens. So if it is a concave lens, we have to get a positive value for simple f. Let's check whether it is going to work that way. Right. So this 4 goes up, it flips. 4 divided by 27 minus 1/27 equals 1/f. 4 minus 1, 3. 3/27 equals 1/4. Sorry, 1/f. So just flip both sides. Simple f equals 27/3. So this is 9 centimeters. So now see that it's a positive value for the focal length. So it is confirmed that this has to be a concave lens. They haven't asked that. You can just simply substitute values and find that. But if you are very familiar with the lenses and done many questions, you should know by just reading the question if it is this must be a concave lens. You need to have that practice, right? If you cannot say those stuff, like if you cannot understand without doing the question, without simplifying that, so that area is lacking. So you need to have that ability to say that, right? Like without that it will be very complicated to know. It will be hard to understand optical instruments and human eye, those is stuff clearly, right? Okay, So the answer is second one for the fourth question. Right, fifth question. In front of a concave lens with focal length 10.8 centimeters, an object is placed at a distance 32.7 centimeters. Image distance is right. So they say this is a concave lens, so the focal length should be a positive value. Object distance, that is for real objects, object distance is always positive, so it is 32.7 centimeters. So those values are given. What they ask is image distance, what they ask is V. So just use a lens equation. Substitute in 32.7 equals, this is positive 10.8. Now simplification, just take it to the other side. 1 over V equals 1 over 32.7 plus 1 over 10.8. Take the common denominator. It is easier to take, denominator should be like this. Then multiply the numerator, 10.8 plus 32.7. So 1 over V is equal to this one. So V, you just have to flip both sides. So V is equal to 32.7 times 10.8 divided by 8, 5, 1 is remaining, 3, 4. You don't have to simplify that. The answers are given without simplifying. So just check for a matching answer to this. Yeah, so it is third one for this one. This is all you have to do is just apply lens equation to this one. Answer is third one for the fifth question. Sixth question. When you look through the concave lens, image of O is seen at the infinity. Focal length of concave lens can be. Okay, so the object is here. You look from here, right? So they say the image is at, when you look here, you see that image of this object is formed at infinity. Meaning the last rays coming to the eye are parallel. That is what it means. They have given the sketch as well, right? They have given a sketch as well. So it is easier now, right? Without this sketch as well, you could get the answer, but they have given the sketch in order to make it a bit easy, right? So these rays are parallel rays. If you get from the sketch, these are parallel rays. Okay. So you can draw two rays like this. That is incident on the convex lens. Those rays forms an image. Here. So you just have to extend this ray, so it forms an image here. And this distance is given as simple A, and this whole distance as simple C, right? So this is the object distance for the convex lens. This is the image distance for the convex lens. When you place the object here, convex lens forms an image at a distance C. First, you have to think about only a one lens at a time. Only a one lens at a time, right? Just forget about this for now. Only think about the convex lens. So it just forms image here by the convex lens. Just forget about this one for now. Right. Then what happens is the image formed by the convex lens, I'll say I1, that becomes object to the concave lens. Image formed by convex lens becomes an object to the concave lens. Right. So this is the object now to the concave lens. Object. We call this, there's no actually an object here. It's just the image formed by the convex lens. But concave lens sees this as an object. So we call these types of objects virtual objects. Virtual objects. Virtual objects. Right. Then the final image, that is at infinity, meaning the final rays has to be parallel rays. So those are the rays that enters the eye. Right. This thing you have to understand, the key thing. So what they ask is focal length here of the concave lens. Right. This is what you have to know. If the rays are parallel, the object should be at the focus. Whenever the rays emerging from a lens is parallel, just remember that. If the rays emerging from a lens are parallel, the object should be at the focus of that lens. So this is the focus. So we learn this stuff in theory notes. So this is called secondary focus. I'm not going to go into details. So the object, this is the object to the concave lens. This is actually an image, but it is an object to the concave lens, virtual object. So the virtual object is formed at focus. Since the image, the emerging rays are parallel. Okay. Emerging rays are parallel. Right. So we know the focus. Now we know the position of the focus of the concave lens. Right. And they further have given this distance, that is the distance between the two lenses. Distance from here to here, it is C. From here to here, it is B. So the distance from here to here, it is C minus B. Right? C minus B. So that is equal to the focal length of the concave lens. Focal length of the concave lens. So the answer should be fifth one, right? So the key point here is like many students don't understand that whenever emerging rays are parallel, these are learned in theory notes, right? Whenever the emerging rays from a lens is parallel, the object is always at the focus. Okay? Object is at the focus. In some cases, incident rays can be parallel. Whenever the incident rays are, it's the same thing. Students know this one. When incident rays are parallel, image is always formed at focus. Right? In both cases. For the concave lens as well. If these are parallel, image is formed at focus. Inverse also is true. If the emerging rays are parallel, the object is on the focus, right? So that focus, we call that focus a secondary focus. This is the primary focus of cells, of lenses. That is a secondary focus. So you have to understand that theory part well. So the answer should be the fifth one for the seventh question. Two rays coming from point O, which is at a distance 1 meter from converging lens with focal length 50 centimeters. This is convex lens, converging lens, and we have this diverging lens. Two rays coming from O, which is at a distance 1 meter. 1 meter means 100 centimeters. So the object is here. The focal length, they say it is 50 centimeters. Emerges from the diverging lens as parallel rays. Okay, now again that is parallel rays. If the gap between the lenses is 10 centimeters, they say the gap is 10 centimeters. What they ask is focal length of the diverging lens. Focal length of the diverging lens. Simple F. Right. So those are all the details we have given. Okay. First, we have to find the position of the image formed by the converging lens, convex lens. So we have to use a lens equation. So without the lens equation also you can find that. Usually in an MCQ they don't give questions to find the lens, to apply lens equation, because it takes some time to simplify this one, right? Anyway, I'll just use the lens equation, then I'll explain you the shortcut method. So what we need to find is V. So U is 100. Focal length, this is a convex, so it is a minus 50. So 1 over V equals 1 over 100 minus 1 over 50. 100 common denominator, 1 minus 2. So it is minus 1 over 100. It is 1 over V. So from that we can find V to be equal to 100. We could have find this without doing any of these calculations. This is how. So you have to check for these, right? In an MCQ, in most cases, the questions they give is like that. So they have given, this is the shortcut method. So they have given 50 centimeters. And the object is at 100 centimeters. 100 centimeters means this should be 2F. This should be F. 50 means this is F. Then this should be 2F should be 100 centimeters. Got it? This is a 50 centimeter, then another 50 centimeters, then it's going to be 2F. So that is equal to 100 centimeters. So just identify that this point as 2F. So in theory notes we learn when the object is at 2F, the image also is formed at 2F, right? That is 2F means 100 centimeters. So this should be 100 centimeters, then this also should be 100 centimeters. Right. Okay, now those are the two ways you can find the image distance. Okay, we'll just use 100 centimeters. So this is 10 centimeters. So the image is formed at here. This is not to scale, okay? This is not drawn to the scales. So this should be 100 centimeters. So that is the position of the image made by convex lens. If you want, we can draw rays like this. After this one, it is these rays actually cannot move. We draw these in dashed lines because we just forget this lens for now. We didn't talk about this lens still, right? We completely forget that for now. So if the image is here, object is here, image is formed at here. This distance is 90 centimeters. 100 centimeters minus 10. This is 90 centimeters. Right. Then this image becomes the object to the concave lens. This is a virtual image. It becomes an object to the concave lens. Object to the concave lens. Since they say the final rays are parallel, you should be able to say the virtual object is formed at focus. This is the secondary focus of the concave lens. Secondary focus of the concave lens. This is the secondary focus. That's why the rays become parallel. Emerging rays become parallel since the virtual object is at the focus. Okay. So now we know the position of the focus of the concave lens. Then all we have to do to get this distance. So it is obviously 90 centimeters, right? So actually you didn't have to do any of these calculations, right? You just find the position. You don't have to do the calculation, this calculation. Then since the rays are parallel, you can say this is the focus. This should be the focus of the concave lens. So once you know the position of the focus, you can say the focal length of the concave lens, that is 90 centimeters. Fourth answer. Right, eighth question. Focal length of a convex lens is 50 centimeters. Its power is, right. So this is the equation to find the power of a lens. There's a minus sign here. In the syllabus, this is the standard equation. But there are other forms of this equation. In some books they might not give this as a plus sign, but in the syllabus there's a minus sign here. So we'll follow the syllabus. I mean, both ways are correct, but the convention is different. So just follow what is given in the syllabus. So there's a minus sign here. So that's the equation to find the power. So this is a convex lens. Since it is a convex lens, focal length is a minus value. So minus 50. Just substitute it here. There's minus sign in the equation. F is equal to minus 50. So minus minus plus, minus minus plus. This is centimeters. So centimeters, I can write it as minus 2 meters, 10 to the power minus 2 meters, because it was centimeters, 10 to the power minus 2 meters, right? So this minus 2 goes up, so it becomes 100 per meter divided by 50. So this is 2 per meter. So you should know that per meter means a 1 diopter, right? You learn this stuff in theories. Per meter equals to a 1 diopter. So instead of per meter, I can put diopter there. Okay, so we got a plus 2 diopters. That is the power of a lens of focal length 50 centimeters. So for usually you have to know that when the power is positive, that is a convex lens. So that is what we got. When the power is positive, convex lens. If it is negative, it is a concave lens. You have to those are the points that you have to remember. Okay, so the answer is fourth one for the 8th question. 9th question. Power of the system made by compounding a convex lens with focal length 40 centimeter and concave lens with 25 centimeters is. So we made like a compound lens, convex length with focal length 40 centimeter. This is a convex. Other one, concave lens with 25 centimeters. So it is positive. So the compound lenses are made like this. So they are together, right? Like intact, like this. So what we have to do is to find the focal length of this compound lens, right? So if you get a question like this, first just find the power of each lens. So I'll find power of this one, P1 minus 1 over F1 minus 40 centimeters. I can write this as minus 2 meters. 40 centimeters is minus 10 to the power minus 2 meters. So 100 goes up. So minus minus becomes plus, minus plus, then 100 goes up, divided by 40. Cancels off, 5 divided by 2, that is plus 2.5 diopters. So what you get is per meter, so it is equal to a diopter. This is the convex lens, P1. Then I go for P2, minus 1 over 25 centimeters. I can write it as minus 2 meters. So minus 2 goes up, it becomes 100 divided by 25. So it is 4 minus 4 diopters. So this is P2. P1 is plus 2.5 diopters, P2 is minus 4 diopters. So what they ask is the power of the compound. So these are the power of each lens. We have this equation to find the power of the compound. P1 plus P2 equals P. So P1 is plus 2.5, P2 is minus 4D. So if you simplify this, you get minus 1.5D. So that is minus 1.5D. So the answer should be the first one for that, right? If I further, we can know some stuff from this. What you get is a minus value here. If the power is minus, lens, the type of the compound lens should be concave. If it is minus, for the question you don't need that, but to further explain that, it's better to remember this stuff, right? It will be useful in MCQs. If power is negative, the lens, the compound lens created by this whole thing is equivalent to a concave lens, since the power is negative there. Power is negative there, right? Answer is first one for the 9th question. 10th question. Between an object and a screen at a gap D, convex lens with focal length f is placed. When D greater than 4f equal 4f less than 4f, number of instances that can form an image on the screen in order. Okay, so this is the another type of questions. So you have to know the theory behind that. So there's a screen and there's the object. It's the object, there's the screen. So we can place lens at different places in order to make an image on the screen. So that's the theory. Usually we keep this distance a constant. We can change the position of this lens in order to make a real image on the screen. So that's what we do. That's what we do. Right? So the focal length is simple f. There's this requirement. In order to make an image on the screen, this is the requirement. I'm not going to prove this. You can check the proof of this on the theory notes. This is the requirement. this distance should be greater than 4 times the focal length. So that's the requirement. So you just have to remember this. They'll just directly ask you, you don't have to prove that. Just remember D should be greater than 4f, 4 times the focal length. So if this is the case, what happens is this creates image on the screen at 2 instances. If this is the case, it creates an image at 2 instances. 2 positions of the lens. Let's say once the lens is here, another position here. If D is greater than 4 times f, the image on the screen would be made when the lens is here and the lens is here, for 2 positions of the lens. Let's say so there are some specialties in this. If this is U and this becomes image distance, just forget about this lens. If this is U, then this is V. Then for the other position of the lens, this length should be V. Then other length is U. So this has like inversed. This is one position. There are not 2 lenses. This is a same lens but placed at 2 positions and at 2 different instances. In order to have this is the requirement. D should be greater than 4 times the focal length. Then we can get images on the screen for 2 instances like this. Okay. Other one is if D equals 4f, there's only one instance. So if D equals 4f, you can only place the lens at a 1 position. There are no any other position that creates a image on the screen. There's only one position for the lens. So it will be like lens is here, U, V, these are equal here. There's only one position for the lens to be placed. If this is the case, if this distance is equal to 4f. If this is the case, if D is less than 4f, there's no way that you can create an image on the screen. Meaning that you cannot create a real image. Only real images can be formed on a screen. Here, in this case, no real image. If we cannot create a real image, we cannot form an image on the screen. Only real images form images on the screen, right? So the answer should be, in this case 2, another case 1, other case 0, 2, 1, 0. Here no images on the screen. Here it can create like virtual images, but in this case you cannot create real images. So as a theory you have to remember this, right? They won't probably ask you to derive these ones. Easily this can be derived, but they won't ask you to derive that. You just have to remember this. Sometimes they check that like 2 instances, D greater than 4f, right? Should be greater than 4f. So the answer to that one is 4th one for the 10th question. 11th question. When a lens P is placed in contact with a convex lens of focal length 15 centimeters, power of the compound lens is 50 over plus 50 over 3D. Focal length of the lens P is. Okay, so we have this length and another lens. It can be a convex or a concave, we don't know yet. So one is f1, other one has f2. Right. one lens that is 15 centimeters, and they say that is a convex 15 centimeter, and it is a convex lens, and the power of the compound is given as plus 50/3 diopters. For the convex lens, I'll just find the power. Let's say P1, that is minus this one, minus 1 over F1 is 15 minus 15 centimeters, so it is minus 2 meters. 15 centimeters means 10 to the power minus 2 meters. Minus minus, it becomes plus. This goes up, 100 divided by 15. So this is 20 divided by 3. This is the power of the convex lens. I just found that. Then I'll apply this equation, P equals P1 plus P2 to the compound. Compound power is given as 50/3. For the convex lens, power is 20/3. Then I can find the power of the other lens. Power of the other lens. So that is the lens P. We still don't know what kind of lens that is. It can be a convex or a concave lens. If you take this to this side, it becomes 30/3 equals P2. 30/3 is 10 plus 10 diopters. So we got a positive value here, meaning that this has to be a convex lens, right? Convex lens. So this also is not a concave lens, it also is a convex lens, because power we got the value as a positive value. Before doing the calculation, we cannot say whether it is a there are ways, but it's better to do the calculation to find the type of the lens. Okay, now we found the power of that lens, but what they ask is the focal length. So just apply this equation again. Plus 10 equals minus 1 over F2. So F2 is 1 over 10. This is in diopters, so this should be meters. You can convert this into meter, means 100 centimeters. Divide it, then you get 10 centimeters. So that's the focal length of that lens. The other thing is this negative sign. So from this you got a negative value, meaning this is a convex lens. Focal length is negative, meaning the power is positive here. You got a minus 10. From this as well, you can confirm that this is the other lens is a convex lens. Other lens is a convex lens. So the answer should be second one, 10 centimeter, and it is a convex lens. 12th question. By a convex lens of focal length simple f, image formed is n times the size of the object. Object distance in this case is, okay, we have the concave lens. You don't have to draw the diagram, I'll just draw it for the clarification. So if this is the object, so for concave lens always the image is formed here. So for any type of object, real object, image is always formed like this. Focal length, they say simple f, n times the size of the object. So if the object size is simple h, image size is n times h. So what they ask is object distance. In this case, let's say object distance is u. So we know this one, v over u equals h over h. So this is linear magnification, right? So h here is nh, this is the object, nh, this is object height, so it is simple h. H cancels off this. V over u equals simple n. V over u equals simple h n. Then v equals nu. We need that. So if this is u, this distance is nu. So I wrote the image distance in terms of u. Then in order to get this one, what we have to find is simple u. So to get this one, we have to use length equation. There's no any other way. Just use length equation. So v, that's a positive value. This is a positive value because image is here. So you get nu minus u. That also positive. Focal length also is positive because it's a concave lens. Right. 1 over n minus 1 over minus 1. You can take 1 over u out. Now it is just a simplification. Put u here, get f here, cross multiplying. So you get u equals f here, f 1 over n minus 1. So that's the object distance. That's what they ask. You can further simplify this. N is the denominator, common denominator. N 1 minus n. So this is the answer. Object distance in terms of focal length and linear magnification. Actually this simple n is linear magnification here. So the answer should be first one for the 12th question. 13th. A convex lens and a concave lens are placed coaxially at a distance 10 centimeters. We have concave lens and a convex lens. Coaxially means like this. And the distance between the lenses 10 centimeters. Focal length of the concave lens given as 10 centimeters. A parallel beam incident on concave lens. On the concave lens there's a parallel beam getting incident on the concave lens. Emerges, then this ray emerges from the convex lens as a parallel beam as well. Right? So meaning that the image formed by this has to be created on the secondary focus of the convex lens. Secondary focus of the convex lens. Right? Okay. So if this is the case, we know that for a concave lens, always images are formed here. Not here. Always the images are formed here. If it is a real object. So let's say the image is formed here. Then I can draw, let's say the image, so the object is somewhere here at the infinity. So the image of that object is made here by the concave lens. Okay, I didn't think about this one yet. So this is only regarding the concave lens. So the image is formed here. We know that images are always formed by this one, given that those objects are real objects, right? Obviously this is a real object. Okay. Then we know the position of the image. What should be the position? If these are parallel lines, the image should be made on the focus of the concave lens. So this is the position of the focus. That should be 10 centimeters. Now we know this position clearly. Next step. Forget about this concave lens. At a time you only thinking about a one lens, right? Now forget about this one. There's only this lens now. right. This image made by the concave lens becomes object to the convex lens here. Convex lens here. So we can draw like a rays coming from this object. Okay, this object, right. Then those rays are the ones that gets parallel. Okay, so someone seen here, observing here, sees the final image of this object is at infinity as well. Okay, so if this, for this to be happen, for these rays to be parallel, this must be the focus of this convex lens, otherwise these won't be parallel. So what's the focal length for this one? Convex. So in this one, focus of the convex and the concave lens are at the same place. So this length is 110 centimeters. 110 centimeters. Oh, sorry. 20 centimeters. This is 10 plus 10, 20 centimeters, right? Not 110. This is 10 centimeters, 10 centimeters, that is 20 centimeters. That's the focal length of the convex lens. So the answer should be the third one for 13th question. 14th question. When an object is placed at 25 centimeters on principal axis of a convex lens, linear magnification of the image is 2 centimeters. Consider the sentences below. Okay. So a convex lens, we don't know the focal length of this convex lens. They say the object is placed at a 21 centimeters. And also they have given the linear magnification, that is 2. Linear magnification is 2. Consider the sentences below. Right. So what they say is linear magnification is 2, meaning the size of the image should be 2 times the size of the object. So if this is simple h, size of the image should be 2h. Okay. So the object, image is enlarged. Its size has increased compared to the object. So in a convex lens, there are 2 ways this can happen. We don't know the focal length. So this is the one of the case. Convex lens can create a real image, inverted real image. So the image distance should be 2 times, because linear magnification is 2. I'm not going to simplify that, right? If it is 2, this should be 42 centimeters. So this is one case. Other case is, if the focus is here of the convex lens, let's say we don't know the focus. If the focus is somewhere here, convex lens can create a virtual image at the back, enlarged virtual image like this. So those are the 2 cases, this one or this one. Both can happen, right? So both are correct. So object distance, it is 21 centimeters. There's another possibility, this also can be, other one should be, length should be 42, because the image height is 2 times. Image distance is 2 times. So the image can form either here like this, or either at the back of the convex lens. So those are the 2 cases, right? So we have to consider both. So what they ask is focal length. So according to this one, I will find the focal length. To find the focal length, you have to apply lens equation. So this is minus 42, right? This is minus because it's to the direction of the light. Minus u is that is a positive value, 21, equals 1 over f. So you get 42 minus 1 minus 2. Minus 3 divided by 42 equals 1 over f. So 1, 4. F equals minus 14 centimeters. Minus means the convex lens, obviously. So this is one of the value. If focal length is 14 centimeter, get it? 14 centimeter, which is focus is here, object is here. So the image can be formed here. So that is one of the answers. Then I'll go for this case. Apply lens equation. Here V is positive, right? Because image is formed at the back of the lens, opposite direction of the light. Light is moving to this direction, opposite to the direction of the light. So it is plus. U is 21 equals 1 over f. 42 denominator 1 minus 2 equals 1 over f. So what you get, this is minus 1 divided by 42. So focal length should be minus 42. So we have 2 values for the focal length. So both are correct, right? According to the answers given, according to the the data given, focal length can be minus 14 or minus 42. So A is correct. B is also is correct, right? C is not correct. In this case, image is inverted. In this case, image is upright. The C should be like here image is real, here image is virtual. Real, this is virtual, right? So C does not match both cases. C does not match both cases. It should match, right? So if we like so it's either A or B. Okay, so it's either A or B. C is obviously wrong. At A, if you further think of this question, the choices given, actually B is correct. Only B is correct. Reason is focal length is 14 centimeter at the first sentence. We cannot say that for sure, right? We cannot say it's definitely 14 centimeters. If we say could be 14 centimeters, then it is correct. We cannot say that it is definitely 14 centimeters. Only B is true because it has could be 42 centimeters. But we cannot say for sure that should be, because it is either this one or either this one, right? So the answer for the 14th question should be third one. It is B. 15th question. Okay, this question could take some time if you didn't follow the the correct simplification, right? Okay, a convex lens is placed between an object and a screen. So the convex lens, the object, and the screen. This object, this is the screen. At two locations of the convex lens, linear magnifications of the image are m1 and m2. So we earlier learned that there can be two locations given that d is greater than 4f for the image to form on the screen. So in this case, if u, this other one should be v. At the other instance, if this is v, then this one should be u. Okay. Let's say this is case 1, this is case 2. These are not two lenses, right? This is the same lens placed at two positions at two different times. So the first case, I'll just say that is m1. They say linear magnification is m1. That is equal to v over u. m1 equals v over u. For the second one, linear magnification m2 equals u over v, right? This is the image distance now. This is the object distance. U over v. Okay, so we got two equations here, v over u and u over v. And further they have given m1 greater than m2. The distance between the lenses is given as simple x. Distance between the lenses is given as simple x. So those are the details here. Okay. So one of the equation, another equation. Then we can have other equation involving x, simple x, right? From here to here it is v. From here to here it is v. Subtract that from u. This distance is v minus u is x. So we got a third combination between these. Here we need to find the focal length of the lens in terms of m1, m2 and simple x. Right. What can we do? What can we do? Okay, I'm just, so you have to get one of the options, right? It will be somewhat difficult, right? Okay, so we have to find a focal length, that is simple f. Simple f, okay? Right. Here I'm just going to, let's say this is first equation, this is second equation. I'm just going to subtract these two. m1 minus m2 equals v over u minus u over v. Denominator is uv, v squared minus u squared. I just did that, right? This is like the only way you can simplify in order to get the answer. So m1 minus m2 equals v squared minus u squared. You can write it as v minus u, v plus u, divided by vu, divided by vu. So we got a combination like this. Other one, I'm just going to apply lens equation for the lens here. Here v is minus value, negative value. U is always positive. Then focal length is negative because it is a convex lens. Just multiply by minus. So vu, v plus u equals 1 over f. So focal length is equal to, just flip both sides, v over u divided by v plus u. Just cross multiply this. Vu divided by v plus u equals v minus u divided by m1 minus m2. Vu divided by v plus u equals v minus u divided by m1 minus m2. Okay. So I'm, instead of this one, this is vu over v plus u, I'm going to substitute it there. You can substitute it there. V minus u divided by m1 minus m2. Right. So what is v minus u? V minus u is simple x. V minus u is simple x divided by m1 minus m2. Okay, now we found the focal length. X divided by m1 minus m1 minus m2. That is the focal length of the lens. Probably, like, if you haven't done this question earlier, you won't be able to get the answer quickly, but you just have to play with the these unknowns and get the answer. It would take some time. Yeah, so the answer for the 15th question should be the second one, x over m1 minus m2.